All right, like I said before, this unit is work, energy, and power, right? So now we're starting to see a lot of these concepts really come together. We want to remember the law of conservation that we talked about when it came to momentum, because it really starts to apply here too in work, energy, and power, right? So let's start going diving deep into here. So this is our end goal, right? To be able to solve a problem like this. So when we have a roller coaster, right? Roller coaster's full of riders and it's approaching a loading dock. So like when the roller coaster is getting ready to like slow down, right? Like after it's at the end of the ride. It's decelerated to a speed and over a distance, and then we want to determine the retarding force that acts upon a roller coaster car. So really a force that kind of makes it slow down. So the goal is to put everything together so that we can actually be able to solve this type of problem. It's a simple problem, but it comes from all the concepts that we did pretty much in of previous units. So let's see how this all works out, right? So some of the topics that we're going to cover in this unit, we have. Can you hear me? Okay. Some of the topics that we have in this unit, right? We have just in general, what is work? Then we talk about power and then how work and power go together. And then we really get into energy after that, right? And then once we get into there, we start looking at the different types of relationships between work and energy and how they play off each other, right? So first, let's get into really talking about the concept. I don't know why I did it like that, right? The concept of impulse and work, right? So when we talked about impulse from the previous unit, right? Impulse was the force over a certain amount of time, right? So force exerted over a certain amount of time, it was a vector and it created a change in momentum. So when we seen an impulse, like somebody just come ahead and throwing something or a short burst of energy, a short burst of change of energy, right? That would be considered an impulse to where it causes a change in momentum. So some type of different action to happen, right? Now work is energy exerted over a distance, right? Over a distance. So what that means is with the work being an energy, the work is a force exerted over a distance, one that is a scalar, and then also too, it's being scaled across of like how much it takes to do something. So like how when you're pushing something, you pushing this thing for about 5 meters, or you lifting something up over 10 meters. So we're not really looking too much over the time, where we're looking at the work is in the distance. So that's the difference. And that cosine part at the very end, work is measured in parallel to the force being exerted, right? So that's where we have to add the cosine of the angle as well too. So sometimes when it's just on the surface, the cosine of the angle just be zero. You'll see like as we get through. So no, we just talked about impulse and work, right? Let's like fill in the blanks for this problem, right? So if an impulse is the force acting over some amount of time to cause a change in momentum, then on the other hand, work is the blank acting over some amount of blank to cause a change in what? So first, I just said it earlier, right? We have our two equations, right? We have work and it's force times the distance. And then we have impulse, force times the time, right? So let's say the first one we have work is acting as a what? Acting over is a what? What would be the first one? If impulse is a force acting over some amount of time, then we say work is a. Now let's look at the similarities between both of them, right? Impulse and work both are equations that both have what in them? What variable? So I'll start it off, right? So with impulse, we have a force acting amount of time. So as work, we're gonna have a force again acting over a certain amount of instead of time, we'll do what? Anybody? All right, I'll just fill it in. So we got work is a force acting over an amount of distance to cause a change in this time energy. So we had change in momentum before, but now work creates a change in energy. So that's the relationship between work and impulse, right? So work, change in energy, because we have a force acting amount of distance. So now we want to decide if the situation example of work and explain why. So let's go through each one, right? So the first one we want to see is if a teacher applies a force to the wall and becomes exhausted, right? So the teacher pushing against the wall, and is that distance that they're pushing against the wall, is it changing? That's the question we have to ask. Because if it is, then we have some type of distance, right? That's moving, right? But the force of the wall, if it's force of the wall is not moving, then we're not really getting any change. So let's think about it. Teacher applies a force to the wall and becomes exhausted. Why? Because you're pushing against the wall's not moving. So we have a force, but there's no displacement of the object, right? So with that, I think I would say that the work is not being done. So I'm gonna say no for that one, right? Now I have a weightlifter for the second one, right? And they lift a barbell over their head, right? So you have the barbell, right? That's the object. It takes some force to put that barbell above your head, right? So you move it, right? So that's going to be the force. It's lift it up, right? Pushing up the weight of the barbell over your head. Now, with that, right? There's a difference in distance between your head, the top of your head, to with your arm extended straight out. So there is some distance, right? So that force is being exerted over some distance. So that I could say, is there work being done? Yes. So if I was to go here, I would say for this one, no. This one, yes. Oh, it's disappearing. So for this next one, right, we have a waiter that's carrying a tray full of meals across the dining room table at a constant speed, right? So it does take a force to hold up pretty much that tray, right? But are we holding up that tray and changing the distance, or are we just holding at a constant, holding it at the same height? Because if we were moving up and down, then we would be changing and having that distance change, right? Now we are moving across the dining room table, sorry, across the dining room horizontally, but that's not where the force is being exerted. One, because it's at a constant speed, so there's no force being exerted horizontally. The force is actually being exerted vertically to be able to coat up the plate. So in this case, I would say no, because the distance that we're holding the plate is not changing. All right, two more, right? So a rolling marble hits a note card and moves it across the table. So now we have a marble that's rolling, right? Then it creates that impact, right? So now we have a little bit of a collision, right? So there's an impulse, right? It's force over some time, right? But now while it does that, right, the note card starts to move across the table. So there actually is some force being exerted on that note card to where it now is displaced and it has a distance where it moves across the table. So that's a force and a distance. So because of that, I'm going to say yes. Then the last one we have a shot put launches the shot. Shot putter launches the shot. So if you ever seen shot put, it's like discus to where they spin around, they're holding it, then they launch it, launch the shot out. And once they do that, the object projectile goes and lands in the air and lands somewhere else, right? So with that, we have a force, which is the exertion to create that collision. So where we see time, boom, the shot is exerted, right? But it goes for a certain amount of distance because that's how we even measure when we're doing like the competition to see how far you get, right? So you have a force over some distance. So that one's I'm going to say yes. I'll see how I did. So for the first one, we got no. Second one, we got yes. Third one, no. Yes, yes. Not too bad. So now with this, right? Just want to kind of put it all together. When it comes to work, right? Fill in the blank with the best answer. But really understanding this, right? I said it earlier that work was a scalar. So we're talking about force over a distance, right? So with work being, let's say, a scalar, right? What would that mean for it to be a positive or negative sign, right? If it's a scalar, we're not too worried about the direction, right? But really what we're worried about is what comes up in this, right? Answer D, right? I'm just telling you because work really is a scalar and it talks about positive or negative when we're thinking about adding or removing energy to the system. Now, I want you to understand that all energy is law of conservation of energy. So no energy is created or destroyed. So we have to say here and say, when we say add or remove, really thinking more of a transfer, right? So what happens when this work goes and is it transferring how energy is transferred to the system, right? But positive or negative really talks about adding or removing, not so much in if it's going to the left or if it's going to the right or direction. Really, just more if we're adding to the system or moving. So let's try and see an example where that works, right? I just want to do this one first, right? Hold on one second. So, and these ones, we're going to look at different scenarios where we see that the work is being done in a positive or negative on the object, right? So, if we want to see if it's being added or removed from the system, right? So, let's go here. Let's look at one being on right here. So, we got an eastward moving car skids to a stop across a dry pavement, right? So it's moving east, right? Then it skids to a stop. So it's moving at some type of velocity, right? But then all of a sudden it comes to a stop. So something had to be working against it to where now it actually changes the velocity that I was moving at, right? So, and you see it skids to stop across the pavement. So it's over some distance, right? So if it was some work being done on that object that caused it to slow down and stop, I would say that that work would be negative. Once again, disappearing. Let me go ahead and change that. Negative. Then let's look at the freshman stands on his toes and lifts a world civilization book to the top shelf of his locker, right? So, in order to take something and put it on a higher shelf, you have to do some work, provide some extra energy, right? So with that, right, we're taking it from a place where it was lower and putting on something higher. So I would say that I would have to add a little bit more energy work to that system. So I'm gonna say that's positive. So now I'll do the next one. We have a roller coaster. is lifted to the peak of the first hill on the shockwave, right? So being lifted again, right? Taking something and put it on a higher shelf. I'm going to say that's adding. Now this next one, the catcher puts out his mitt and catches the baseball, right? So if you're catching the baseball, they throw these baseballs at like 90 miles per hour, right? So if you're the catcher, you have to pretty much make sure it gets in the glove, right? So then you can go ahead and catch it and throw it somewhere else, right? But with that, right, you're stopping something from going 90 miles per hour to be sitting still in a glove. So now that sounds like you have a force working against the object. So where now over that distance is slowing down to sit in there. So I'm going to make that a negative. Lastly, we have a falling parachutist opens up the chute and slows down, right? Same thing. Gravity is pulling me down because I'm in the sky. I'm skydiving, right? Then I throw my parachute out, and then boom, I start to slow down. We talked about this in the previous unit, I think unit 2, or vectors, I think, whichever one that we did, air resistance. But yeah, that air resistance goes across sectional area, goes and hits the parts of my parachute, so where then it creates to where I start to slow down and I hit that terminal velocity so I can reach a nice safe one to kind of land, right? But with that one still, I would say negative. So let's see how we did. Negative, positive, positive, negative, negative. Good, right? So what we want to focus on, right, is work is negative when the force and displacement are in opposite directions. Any questions on that so far? Hearing no questions, give me a thumbs up if that's all right, if everything's making sense and you're doing good so far. All right, I got one thumbs up. Two, good. So now we talked about work, right? And we want to actually calculate these, right? Just a quick calculation of work being done on each system, right? So now we have our equation. Let's just try and see mathematically, we try and put it together. So for each situation, we calculate the amount of work being done by the applied force, right? So let's look at the direction of the applied force and then see if we can calculate the distance that's being done and find the work, right? So we have 100 Newton force that's being applied to a 15 kilogram object, horizontal distance of 5 meters at constant speed, right? So let's do that first one. So we have an applied force. So we have a force, and we'll do it like this. Clear. So you have applied force over some distance, right? And if we were talking about the angle, right? Let's look at that angle. And this will tell us our work. So the force that we have is 100 newtons, right? And that's over 5 meters. Now, if I'm looking at the angle at which this force is being applied, it looks like it's directly to the right. So if we go ahead, go back to like our unit circle, right? This would be 0. It's 90. It's 180. 270. So this is where this vector stuff came in handy, right? So now we're at 0 when we're directly to the right. So it's going to the right. So this is 0. So I could put 0 right here, right? I know, though, that the cosine of 0 is equal to 1. So now if the cosine of 0 is equal to 1, this is basically just 100 times 5, which equals 500. And the unit for work is joules. So we got 500 joules for our work, right? So that's really all you do. Now, how does that change if we have it at a slant, right? Let's look at it. For this one right here, right, we still have the same formula that our work is equal to our force times the distance times cosine, right, of the angle. So this one we have the same 100 Newton force, right, but it's applied to the angle to horizontal, right, and our object accounts me for 5 meters, right. So same thing, right. We got 100 over 5 meters, but this time the cosine of the angle is 30, right. Now remember, I don't know if you guys remember this, right, but remember this triangle we had? 30, 60, 90. This is from our vectors unit, right? We got 2x here, then we have x, and then we have across in there x root over 3. So across from 30 is the x, right? So if I know this is 100, right, then I can say that you could do force times the cosine of this. This would be half of that, so it'd be 0.5. So this is 0.5, right? Yep. So cosine 30 is 0.5. And would it be in 0.5? I do 100 times 5, that's 0.5, so over 500 divided by 2, pretty much, was equal to 250. But really the most important part, not the calculation, but being able to see that because of the angle that when I'm pushing at, the applied force, I have to account for that into my work calculation. So let's do one more, right? So now we have the upward force.
How'd you get 0.5 again?
Cosine of 30 is 0.5, right? $30.
No,
Is it 0.8?
it's 0.866.
Oh, I was wrong. Oops. Oh, wait, no, I know what I'm looking at. Obviously, yes. Wait, hold on. Cosine of 30. Yes. I looked at it the wrong way. I did the triangle right. Cosine of 30 would be this one over here. So whatever x is, right? So this was 100. So this would be 50. And then this would be 50 times root 3. So 0.886. Yes. So now we, instead of here, let me just erase this. So now when I come here, I'll actually use my calculator. I'll try to do it in my head. So this would be 433 about. So now I'll do the same thing for this last one. You want to find the work applied to lift this object to a height of 5 meters, right? So we still have to find a force, right? Over some distance at an angle. Now, the first thing, right? We're pulling this straight up, right? So if we look at the angle that we're pulling it up at, we got, let me say, because I don't want that to be. Technically parallel to it, it would be 90, but just for the sake of it, because the cosine of 90 is 0, I don't want to do 0. So we're going to just treat it as pulling up as just treating it parallel. So we're going to just say it's 0. So we just have 1. So I'm going to say that angle is 0. Just because if I put 90, obviously if it would be 90 directly, it would be equal to 0, but there's work being done pulling it up. But then that brings us to this point, right? We have a distance, right? Which is 5 meters. This ends up being 1. But now we need to figure out what our force is. What is our force? Is there a way that we can calculate our force? Now let's think, right? Technically, if I was to draw the free body diagram, right? We have some applied force that's pushing it up, right? But what's putting it down? The weight due to gravity, right? And we know that the weight due to gravity is equal to mass times gravity, right? So to be able to pretty much lift this force up, right? We need to be able to lift up the weight of this object for 5 meters. So let's take that force and actually make it equal to the weight of the object. So let's do the mass, which is 15. And then we're going to multiply that by gravity, which is 9.8. And that over a distance of 5 meters. So we put that all together. We're at about 735 joules. $500, $433, $735. All right. So we did okay. The whole thing with this is really just looking at the different angles at which the force is being exerted and how we count that into the equation, right? Still pulling some of the stuff from before, right? That 30, 60, 90 triangle came back, and also using the free body diagram from unit 2 to be able to understand the forces. Like those still came back to help us out. Like all these different concepts from units 1 through 5 are really starting to come to this very one at 6 too. So this is where you start to see the correlation between all the stuff that we did earlier and what we're starting to learn now. Now we're starting to get into talking about working a little bit of energy stuff, right? All right. So as I'm looking, this will be our last problem of the day, right? So let's take our time with this one. So we really want to calculate the work being done on each force and then find out total work being done in the situation, right? So remember what we said earlier about deciding if something is positive or negative, if we're adding or removing to the situation. That's what we want to kind of take into account here. So we want to find the individual works, right? Hold on. I realized I did that. and find the individual works, and then calculate the total work, right? So let's start looking in these first ones, the first scenario, right? So we got a 10 Newton force that's being applied to a block, right? Across, so no friction, surface, for displacement of 5 meters to the right. So let's see. So first we have, real quick. Now this is where we take into account the different angles, right? So we do have a force, right? So we have a force over a distance. What is the force? 20 newtons. Oh my gosh, the disappearing ink. For how long? How far? 5 meters, right? Now let's do the same thing. We have the force applied. We have 10, and that's for 5 meters, right? Now let's do another one. I'm just going to just kind of draw it down here. We got the weight due to gravity. That's the force. And that's over 5 meters. So it's still over 5 meters, right? But here, when we start to see things to get to positive, negative, and differences, right? When we start adding the angles, right? So remember our unit circle. 0, 90, 180, 270, right? So if I look at my first one, norm, right? That's at an angle of 90. Parallel to the horizontal, right? This force applied, I would say, is an angle of 0. And the F grab is at an angle of, let's say, 270. So when I look at these, right? Before I start calculating, let me just look at that cosine, right? I know that the cosine of 90 is equal to 0. So that means that no matter what that force over that distance is being done, that F norm really has no work being done around it because it's actually not parallel to the surface of which it's moving, right? It's perpendicular. So that means that this entire chain up here is going to end up being 0. Same thing for this last one. If I go ahead and look at F grav, right? The work being done is actually not parallel to the surface of where it's moving at. So over the distance, right? So it counter is perpendicular. So now we have another one of 0. And you get the same thing because if you put cosine of 270 in your calculator, you should get 0. So now all we're left with is the middle where the cosine is equal to 0 because of the angle is parallel to the direction it's moving, right? Cosine of 0 is 1. So we could just ignore that. Then we got 10 times 5, which is 50. So when we add all these together, we have 50 plus 0 plus 0. So we have a total work being done of 50. All right. So let's take just a quick 2 seconds, right? I gotta see you guys there, right? I'm gonna do just 2 breakout rooms, right? I just want y'all to work out together. Just work together, and then someone come off mute and explain your answer. And I'll tell you which one you want. Do B and C. Just try it out. Come back in about 5 minutes. I just reshared it. Can you see it?
Yeah, but not as well. It's a little tiny.
Hold on.
Yeah, it's blurry.
Hold on. Is that better?
Yeah. There. Thank you.
Oh. All right. My first group, what did we get for B?
Uh, let's see. 0 and 0 for the normal and the gravitational one, and then -50 for the friction.
So with that negative, what does that negative really mean?
It's going in the opposite direction.
Opposite direction, or what's going on with the work? Is it being added or removed to the system?
Removed?
That's what we want to remember, right? Added or removed when we're talking about positive, negative, because work is technically a scalar. Not so much about direction. Work is a scalar. So when we talk about positive, negative, adding or removing. Now, for those other forces, you got 0. Why did you get 0?
I just basically looked at the first problem, and it's all the same numbers.
Now, what you understand and using the math, right? Now, think logically about what 0. What was the angle that you got for the first numbers? For the first those other ones, the other forces.
90, 90, because they're like up and down.
So you got 90, right? 90 compared to 0, right? Would you say those are parallel or perpendicular?
Perpendicular.
So when we talk about work, right? Work is parallel to the force, right? The direction of the force, right? So when we have a force that's perpendicular to the direction of where it's traveling, right? Then it doesn't have an effect. Remember, we said perpendicular components are independent of each other. So by you seeing that angle that's 90, right, and it's being perpendicular, that's where you get that 0 from. And it shows with the math a cosine of 90 being equal to 0. So I just wanted
Yeah,
to make sure. Go ahead.
that makes sense.
I just wanted to reinforce that. Okay. My second group, did we get anything for C? Anna, do you have anything for C?
Was that our group?
Yes.
Well, Cindy had it, but she said her computer froze.
You want to try it out real quick?
Give me a sec. She said she was gonna send it.
So does this mean basically the up and downs is mostly always 0 for everything?
You gotta think about it. Depends on the situation, like where the distance is, right? So think about an elevator. Would the up and down be 0 on the elevator?
Oh yeah, no. So only if it's like, okay, that makes sense.
Let's try and just do it together. I don't think it's much different, right? So we have a 10 Newton force being applied to a block to push a block across a fictional surface. So we're still pushing against a surface, right? At a constant speed for a displacement of 5 meters, right? So we still know it's very consistent. Everything's 5. I just write a big 5 right here. Oh, that's 5, right? Then we have our different values. So norm, we have 20 newtons. I'm just filling stuff in. The applied is 10. Weight 20. And then friction 10, right? Now, when we really start to see this is when we talk about these angles, right? So we already know norm and grav, right? 90, 270, right? And then we know that both of those are going to make cosine equal to 0. So then the whole thing is 0, right? So now let's look at these two applied forces, right? They're both at 0 to the right, parallel to where it's moving across the surface, right? Good. So now we're seeing that, right? We want to see what these values, right? So we have, what is it? Oh, both of these are, actually, I wrote this the wrong way. This one should be 0. And then this one, I was moving too fast. Sorry. Because I wasn't reading. This one is 0. This one is 0. This is 270. And then this one is 0. So now with these both being 0, the cosine of 0 is just 1, right? So then we could just go ahead and we could do 10 times 5, which is 50. And 5 times 10, which is 50, right? But what we need to do is see, is it being added or removed from the system, right? So what we're saying is it's being added, right? The force. Somebody putting a force onto an object. When we talk about the applied force, think about it's going to the right. Applying force to push it, right? But what's working to remove that energy or work against the system will be the force of friction, right? It's in the opposite direction, which means that we're going to have it to where it's slowing it down. So that work from the friction is actually removing from the system, right? So we make that force of friction, that work with friction, minus, and then we make the applied force positive. So then the end we have 50 and minus 50, which gives us a total of 0. Does that make sense? Give me a thumbs up if that was okay. Anybody confused? I haven't seen a thumbs up. Let's try and see with this next one to see if we see any similarities. And this will be our last one for the night, right? So we have a 2 kilogram object and sliding across at a constant speed across a frictionless surface for a displacement of 5 meters to the right, right? So it's sliding, right? But by our free body diagram, we have just a normal and grav force, right? So this one is 20. This one is 20. And we know it's still for 5 meters. But now what is the angle that we're looking at for these? This one's vertical, so it's 90 because the surface is horizontal. Then this one is 270. So what we see here is both of these end up being 0. So now we have 0 for this. So our total is 0. What does this problem really show us? That when the forces are not parallel to the movement of the object or the surface that the object's moving in the direction, right? Because we're looking at that distance, the work caused by the forces end up just being 0. That's why we have the cosine. So let's check our answers one last time. Pretty much the same thing we got there. Really just that positive and negative is adding or removing to the system. Any questions on that? All right, so I'm gonna stop there for tonight because this is a new topic. We're gonna come back on person on Monday, but once again, just catch up on any work, review a little bit of, watch over this video clip. I'll upload it over this weekend. But this is just the first part of work, power, energy. So we'll try to talk about more power, energy next class and try and see how far we can go with those connections and see where we're at. But I'll see you guys on Monday.
Thank you.